Okay, now that we've covered some of the basics of Lyme and some of the concepts, let's get in a little bit more to the practicality piece and think specifically about Lyme recommendations. Okay. Before that, we need to kind of introduce a few concepts, and we've already talked about soil buffering or buffering capacity. And this is a really important concept when we're thinking of pH. We can apply it to other nutrients as well, but it's this idea that it's particularly relevant for pH and the ability of the soil to resist essentially changes in soil pH. Okay, so a buffer maintains the solution pH when small amounts of acid or bases are added. Okay, and so when some acidification event happens or an event that's going to raise the pH, the extent of that pH change in the soil relates to the buffering of that soil or the buffering capacity. So it's more conceptual. I mean, we can measure it, but we think of it as a kind of a broad concept. Now, soil behaves like a weak acid that will buffer pH, and as that buffering capacity increases, typically that's going to coincide with CEC. So as CEC increases, the clay and the organic matter content increase, typically buffering capacity will increase as well. So, and then the quantity of clay minerals. It's not just the amount of clay, but it's the actual mineralogy of that clay. What types of clays are there? Again, 1-to-1 versus 2-to-1 in a broad sense. Determine some of the buffering in soils. Okay, and sandy soils, low CEC soils are poorly buffered. That's the converse. And it's important to differentiate between active acidity and potential acidity. Okay, so what does that mean? Well, active acidity represents the actual physical quantities of hydrogen and aluminum concentrations in the soil solution at any given time. So it's literally the pH at any given moment. On a soil test report, soil pH represents that active acidity in solution. And then there's this concept of potential acidity, right? So soil pH measurements that deal with the ability of the soil to buffer against pH changes has to do with this potential acidity. So in other words, the active acidity is the pH at any given moment, and the potential acidity is more related to kind of the function or the structure of the exchange sites and the ability of that soil to resist pH changes. Okay, so we measure, these are more concepts, right? But we measure this with two indicators that are very common on a soil test. Okay, so soil pH versus buffer pH. Now these are easily confused, of course, because of the names, but they're different in terms of what they actually reflect. And so soil pH, again, measures that active acidity. It's a measurement of the solution concentration of acid, of the hydrogen and aluminum concentrations in that soil, okay? And it's typically done, you'll often see a 1-to-1, usually most commonly done, say, in Ohio or the north central region, the Midwest. 1 part soil, 1 part water. You slurry that solution, you put in a pH electrode which measures pH, and then you have the actual soil pH, okay? In contrast, we have this buffer pH, okay? So, and it's sometimes abbreviated as like capital B pH. And this measures the ability of soil to resist a change in pH, right? Again, that idea of the buffering capacity of that soil, that's hence the name buffer pH. So we measure this empirically in the lab by taking the initial pH reading, like we just described, 1-to-1 soil to water, and then we add a small amount of buffering solution. And this buffering solution is really just like a calcium chloride lime solution. So we're adding something that simulates adding lime to the soil to neutralize that acid, okay? So the idea then is that we're going to lime this little soil in a beaker in the lab, and we're going to see what pH change that is, okay? So if the difference in pH is large, if that difference is large, it means that the the pH of that soil can change easily, and that therefore the soil is poorly buffered and a low lime rate is needed. So if the difference between the initial pH and the buffer pH is small, that it means that the soil pH is highly buffered and a higher rate of lime is needed. So this, might take a little bit of kind of thinking through, but it's very important, and that we don't confuse this idea that when the soil is easily changed, right? Like the pH, if we add a little bit of lime and that pH changes readily, then we consider that a low buffered soil, and that because that it changes easily, we don't need as much lime, and the converse is true with a highly buffered soil. Okay. Now, historically in Ohio, we've used what has been called the SNP Buffer. This is work that was actually done at Ohio State. Shoemaker, McLean, and Pratt were soil scientists here. And that was kind of like the gold standard for a number of years. And since then, at the University of Kentucky, Frank Sikora introduced a buffer that doesn't have chromate in it and was intended to be a non-toxic mimic of the SNP Buffer. And this has really been widely adopted by most commercial labs. So most commercial labs in Ohio are using this Sikora buffer, but it's intended to mimic this SNP buffer. There are other buffers that serve this purpose depending on where you're at in the country and what lab you're dealing with. So common ones would be the Woodruff, the Adams-Evans, and the Malick buffer. You go into, say, Pennsylvania, if you're from the eastern part of Ohio, a lot of our Ohio soils go to the Penn State soil testing lab, and they'll use a Malick buffer for determining this. Caveat, kind of older nomenclature, but LTI, or Lime Test Index, is essentially the buffer pH times 10. So I actually kind of prefer this because it helps draw any confusion away. If you've got a pH of 6.5 versus a buffer pH of 65, it helps kind of differentiate those. But that's really fallen out of favor in the last, say, 10 or 20 years. And so most people don't really report Lime Test Index. They just report it simply as buffer pH. Okay, so, and it's important to understand that these buffers don't always mimic the same thing. So the Malick buffer has a kind of an equation that's associated with how much lime you need depending on what the buffer pH value is. And that's actually a little different than the SNP buffer. So, just recognizing that when you're dealing with buffers, if you're changing between them, they're not always the same thing, and they're not going to generate the same lime rate. Okay, so there's a number of factors that go into determining the lime that you needed or that you need. Of course, the initial pH of that soil, what pH you'd like to move that soil to, that's of course going to be crop dependent. We already talked about the buffering capacity of the soil, which is highly related to CEC. And it's, I guess, important to point out that most soil testing labs will commonly report how much lime to apply, right? So that's usually not an issue. Here's just a schematic showing lime rates, how much lime you added versus the pH, okay? So imagine we have a pH of, say, 6, and let's maybe say a pH of 6.5, right? And then we've got a soil with different CECs from a 5 to a 10, a 15 to a 25, okay? So the idea is that if we start at a 4.5 and add 2 tons of lime, it might raise the pH of a heavy clay soil to 5.5. But if we apply 2 tons of lime to a sandy soil, it might raise it above 7, okay? So this idea, this relationship that as our CEC increases, the buffering capacity, the ability of a liming event to change the soil pH drops as that CEC increases. All right, so let's talk about lime for a second. Not all lime materials are created equally. and they differ in their ability to raise the pH. So from a chemical standpoint, all lime can be rated as a calcium carbonate equivalent. So that's the neutralizing value a lime material has compared to pure calcium carbonate. So calcium carbonate pure has a reference value of 100. So the CCE, the calcium carbonate equivalent, is 100, right? They just put this in a percentage term. You can think of like calcitic limestone, because it's not just pure calcium carbonate, has a a calcium carbonate equivalent of somewhere between 80 to 80% up to the full CCE, depending on a number of factors of that material. Okay, and you can see some things like wood ash have a pretty low reaction chemistry compared to our standard. So this just provides a way. This CCE, this calcium carbonate equivalent, provides a way to standardize between the chemistries of these different products. Okay. Well, that's not too bad, but wait, there's more. We also need to think about the effectiveness of lime, not just in the context of chemistry, but some of these other things. And so we need to think about the fineness of the material, the purity of that material, and the moisture content. And it's really kind of the purity and the fine, all three of these things go together to kind of make up what the behavior or how the ability of that lime to neutralize acid. So let's talk about fineness factor, right? So fineness factor is really how much this product has been ground. Most of our lime that we apply in Ohio comes from mined limestone quarries. So it's literally the process of taking, grinding soil out of a giant hole in the ground. And then they either take it, it can be crushed limestone, it can be gravel, and then it can get ground into finer and finer sizes. These are rated based on how much the mesh size that they pass through. And not surprisingly, taking material from here, 3/4 of an inch to a 1/4 inch, doesn't cost as much as taking from 3/4 inch to 200 mesh. This is really essentially a powder. So the processing that's involved in reducing the particle size significantly adds to the cost of this. And so we think, we understand that there's some scenarios when you want, it to be as fine as possible. That's going to react faster and with the soil than, say, some of these larger chunks. Ag lime typically has a mix of different size fractions that are kind of blended together, so we get fast action and then some more slow and sustained release and activity, and that's what these larger chunks do. These larger bits are going to provide a more slow release, if you will, neutralizing effect. Okay, so like we just mentioned, the smaller the mesh size, the faster that lime is going to react. Okay, and so this is what this graph is just showing. Not surprisingly, that this is intuitive. If we grind something up and make that the surface area to volume ratio really small, it's going to react really quickly, and a lot of that's going to be available. So that has a big thing to do, a big part of the ability of that lime to neutralize acid effectively. Okay. So in Ohio, and this is kind of a little bit obnoxious because there's a lot of different permutations of this, and it's just a function of kind of historical reasons and not standardizing this across states. But essentially, if you are in Ohio and you want to sell ag lime, if you want to sell a lime product and label it as a lime product, you need to go and essentially go through some credentialing and get your product an ENP, an effective neutralizing power. Okay, and so that's why a lot of people don't bother doing that, and they'll say, "Oh well, we didn't go through the proper channels. We're just going to sell this amendment thing that might be a waste product, or might be a byproduct of chicken eggs or whatever it might be, slag lime from a steel mill." And so they say, oh, it's got liming action, it helps neutralize acid, but we're not really officially rating it. And so that becomes challenging to manage. And if growers ask me or ask other, consultants or county educators, well, how much should I use? Well, it hasn't been officially rated, so it's hard to really know that for sure. So the ENP, similar to what we just talked about, takes into account the chemistry of that material, i.e. the total neutralizing power, the fineness of that grind, and then the percent moisture. Okay, so how much water in it. That the moisture has, of course, to do with like the purity of that material. So this is all registered through the ENP is generated at a test lab that is registered with the Ohio Department of Ag. But again, ODA calls them effective neutralizing power. Indiana calls it a relative neutralizing value, and Michigan a neutralizing value. So how's that for being a bit obnoxious? I'm not entirely sure about Kentucky and Pennsylvania, but this isn't standardized to the extent that we really would like. The reality is that all these have the same pieces in there. They have the chemistry of the material, the fineness, and the moisture, which may or may involve kind of the purity of that material. How much of that material is actually lime versus other things, whether that be water or whether that be some impurities, etc. So every material, again, that is sold as lime in the state has an ENP, and you should, if you're buying lime, you should be able to ask for this, and the retailer should be able to supply you with this. Okay, so ENP, effective neutralizing power, is reported in pounds per ton. So something like ag lime that's super fine has an ENP of 2,000 pounds per ton. Okay, and that's essentially our standard, which these other materials are measured against. And you can see that some things, dolomitic hydrated ag lime, has a greater neutralizing power. The higher this number, the more effective it is as a liming source. And some things like wastewater lime have much, much lower. So, this wastewater lime is essentially a 25% or a quarter of the neutralizing power that our kind of standard ag lime would be. Okay. Here's the formula. The formula for calculating ENP, you're not really responsible for that. This is going to come standard, but if you're interested, here it is. And again, here are the three components. The chemistry of the material, the fineness, and the moisture content are the three pieces that go into calculating this ENP in Ohio. Okay, so let's talk real quick about developing a lime recommendation from a soil test. Now, if you get a soil test back, there's a lot of different information that can come from it, and there's no standardization in terms of how soil test results are reported. So it depends really on kind of the lab that you're working with, and what their reporting format is. But here we can see a soil pH and a buffer pH. Okay, so the soil pH is 6.2. and a buffer pH is 6.9. Now these are not the same value. They could be the same value. They might not be. Okay. Here's another example of kind of soil test results. Here we've got a soil pH of 6.1 and a buffer pH of 7.1. So a whole unit different. And here we have a soil. This is soil from Defiance County. Here we have a soil pH of 7.0. Well, where's our buffer pH? We better call the lab up and complain that they haven't given us a buffer pH, right? Well, the reality is the soil is already neutral, and so there's no reason to provide a buffer pH. The buffer pH drove this pH above 7.71. Some labs have different cutoffs when they will or won't report that. But having a buffer pH of 7.5, for example, is not particularly helpful, because what I haven't told you right now is that we really use this buffer pH value to generate a lime recommendation. Okay, so the soil pH, again, is our active acidity. That's what the pH of that soil in solution at that point in time. And then the buffer pH really just feeds into this lime recommendation. So it tells us empirically, when we add a teeny, it's essentially like, imagine, just think of it as like you're just doing a little microcosm experiment where you take some soil, you add some lime, and you add a set amount of lime to a set amount of soil, and you see what the pH change is. That informs us what our buffering capacity of that soil is, the ability to either change or resist change. Okay. So let's talk about how we actually do this. Okay. Well, I'm going to post agronomy guide and a table here. This table is replicated a few different ways, but it's very easy to read. We simply have the buffer pH of a solution, right? So this is the actual. Now we talked about change in values from the soil pH to the buffer pH. There's no real subtraction or any difference that's calculated. It literally just reads what is the value, what is that pH value after you add that lime buffer. Okay, so in the case of Ohio, it's often Socorro buffer. And so we get values from 6.8, 6.7 all the way down to 5, right? And it can go below that even. And so the way we do this, say we get a soil test back and we have, buffer pH of 6.5, then we read across and it's going to ask you what's the desired pH level. Well, say we're working with a mineral soil, which is most common soil we find in Ohio, especially ag land, and we wanted to raise it to a final pH of 6.8. That's going to tell us 2.9 tons of lime. Okay. If we want to raise it to 6.5, it's going to tell us 2.5. So the pH, we're not raising the pH as much, and because of that, our lime rate goes down. And then conversely, to 6, it's going to go from 2.5 to 2. Okay, this is for more special types of soils. These are organic or muck soils, but we read this in the kind of the same rate. So we say a pH. Here's our soil. Oops. I don't know why I keep doing that. The soil pH and kind of our final pH. Okay, so that's a bit of a special case scenario. These organic soils, they're managed differently. And we'll maybe get into that a little bit more later in the semester if folks are interested. Okay, so here's the example, right? And this is kind of a realistic scenario. You get a soil test back indicating that your pH, your soil pH is 6.0, and that your buffer pH is 6.6. You decide you want to raise the soil pH to 6.5. So you're saying, oh, it's a little bit below optimum, and I want to raise it to 6.5. Okay. So then you go and you call around, and you check retailers and say it's the same retailer. They have material A with an ENP of 900 pounds per ton. Say it costs $14 a ton. And then material B has an ENP of 1,500 pounds per ton and it costs $20 a ton. Okay, so we need to ask the question of which one to apply. And as farmers, we're always thinking about running a business, and what are the economics of this kind of decision. Okay, so let's walk through this kind of typical scenario that somebody might encounter and generate not only a lime rate, but figure out like which one should we apply. Okay, so the first step is to use the agronomy guide or soil test results to determine lime application. Now let's go back, and again we'll say that our soil pH is 6, our buffer pH is 6.6, and that the desired level is 6.5. Okay, so we'll go back. Our buffer pH is 6.6. And we want to, which is right here, and we want to raise our pH to 6.5. Okay, so here we go. We just read across here, 6.6, buffer pH 6.5 desired level. That gives us a 2.0 tons of agricultural limestone per acre. Okay, so that's our basically our answer that's our lime rate of 2 tons per acre. So that's fine, but now we need to understand that that's with kind of the standard ag lime, but that's not what we have access to. So how are we going to calculate what our lime rates are for these? And so that's the next step. We need to calculate how much material we need to apply to equal 2 tons per acre of lime for each material. Now here's the equation that we're going to use. Tons of material per acre equals our LR, which is our liming rate, times 2,000 divided by the ENP. So we're essentially setting this ENP equal to our standard of 2,000 and then seeing what that gives us, okay? So here's the equation for material A, and again we can go back and look at material A is 900 pounds as an ENP, okay? So we'll go back and we just plug this in. Our liming rate, our LR, is 2 tons per acre. We're going to multiply that by 2,000 pounds per ton divided by our ENP, which is 900 pounds per ton. The pounds per ton cancel, we do the math, and we get 4.4 tons per acre. So that's our liming rate for material A. We do the same thing for material B. Again, it's the ENP this time is 15 pounds per ton. Our liming rate doesn't change. It's still a 2-ton recommended application rate, but we need to account for this lower ENP value. But it's it's higher in material B, but lower relative to this standard. And so again, 2,000 divided by 1,500 times 2 is 2.7 tons per acre. Now this makes intuitive sense, right? Because if our ENP is lower than the standard 2,000, and so we get essentially a higher lime rate than what our higher total lime rate with that material than our standard lime rate would be if we used kind of the gold standard of ag lime. And here, because it's greater, the 1,500 is greater than 900, it's still less than 2 ton, but lower than this 4.4. So that makes intuitive sense. So just check this to make sure, check your math and plug the equation in, but just think through this and say, does this make intuitive sense? Our ENP, if it's less than the 2,000, then we're going to get a net liming rate with that material that's greater than what your liming rate that table generates. So hopefully that's clear. So now we have the tons we need per acre, and finally the next step is to calculate the costs of material on a per ton basis. Okay, so from the last slide we take this 4.4 tons per acre and we multiply it by that cost that we said, which was for material A, it's 14 tons, and for material B, it's $14 per ton. For material B, it's $20 per ton. So we multiply that across, and it looks like material A is $62 per acre, and material B is $53 per acre. So, there's, of course, in the real world, there's logistical constraints to all this, but when we consider the trucking costs, the equipment constraints, the ease application, the calcium magnesium level, so that's an important consideration. What's our calcium magnesium? What type of lime are we applying? Does it have calcium or magnesium? If all these constraints are equal, then material B is the cheaper option, and we can calculate exactly how much we should apply to neutralize the equivalent amount of acid that material B would and the equivalent amount of acid that this kind of standard ag lime would represent. So that's really how we come up with the lime rate, and we'll have a little bit. I'll provide a fact sheet that you can dig a little bit more into these details and get a second look at some of the same type of material. Okay.